Alrighty, we're going to talk about the central limit theorem. So we're going to take a look at samples of X bar from a population and how they distribute. In other words, what their graph looks like if we take a lot of samples of sample means. Does that make sense? So here we have a population. Let's just say our population, we'll do coins. So I'm going to draw my axes here. And we'll talk about the age of coins. So this would be 0 years or this year's coin. And we'll say this is from 1970s. That's 50 years old. So we can kind of figure out there are more coins in distribution today, right? The newer coins are, there are more of them out there in circulation than there are the ones from 1970. So the distribution, I would assume, we can make it a little jagged because, you know, nothing's perfect. But the distribution probably looks positively skewed. So somewhere in there is the mean. The mean is, we're going to say it's about right there. We're going to say about at 20, about 20 years old. All right, we're going to say the mean is 20 years old. So if I took samples of pennies, now there are millions and millions, maybe billions of pennies out there. And if we took samples of size 2, so let's say we got a 50-year-old penny and a 0-year-old penny, that's this year, and we average those out, we'd get a 25. Now we'll say that's about right there. We'll call that X bar because that represents a mean. And then another year, we have a 10-year-old coin and we have a 30-year-old coin. So 10 plus 30 is 40, divided by 2 is 20, and that mean would be right there. So if I start doing these samples of size 2, I'm going to get a nice variable distribution. I could have a 50 and a 40, and it ends up over here, but more than likely, my distribution's going to, if I stack them like a dot plot, my distribution's going to look like that. My distribution of means is going to look approximately normal within that distribution. Now, if my sample size is big enough, so if I took samples of size 30, so not just 2 pennies, but let's take 30 pennies at a time. So let's erase this. Let's take 30 pennies at a time. So I have my distribution of the population of pennies. We'll say it looks like this, from 0 to 50 years old. We've got our mean for the pennies, for the populations about right there. And if I took samples of size 30, we're going to get a tighter distribution because everything's going to be closer to the truth. Think about that. The bigger my sample, won't our values be more accurate, right? If I sample 2 people, do I get the truth? Or if I sample 30, well, I'd be closer to the truth. Or if I sample 100, I'd be even closer to the truth. So the larger we sample, the closer it looks like the truth. All right, so they're going to be centered at the mean. But now this time, this distribution, it looks a little more approximately normal, a better shape. It's going to look like that. A little more tighter, the standard deviation is not as spread out. But those are a bunch of sample means, right? I took 30 pennies and I got their mean. Let's put that X bar down. I take 30 other pennies. I find their mean. We'll say it's that one. I take 30 other pennies. I find their mean. It's that one. I take 30 other pennies. I find their mean. We'll say it's that one. So we get this distribution of sample means. This is means of the pennies that we have from this. What's the smallest number that we can have in our sample size to make this nice approximate normal distribution? Well, that's size 30. Once I hit 30, 30 is kind of the magic number in statistics. So if I can get samples of size 30, the distribution of sample means will be approximately normal, and it doesn't matter how the population looks. The population can be shaped like a V. It can be shaped flat, constant. But the distribution of sample means will be approximately normal. So up above, I have this important item in statistics. This is called the central limit theorem. If a sample size is sufficiently large, and we'll say that large is anything bigger than 30, then the distribution of sample means, X bar, will be approximately normal regardless of the shape of the population distribution. And that's what we've shown here. So we've got this population of a strange shape, but when I take samples from this population of size 30 or bigger, those sample means, if I take many of them, will end up looking approximately normal. Okay, so that's what the central limit theorem is. When I use the central limit theorem, our z-score changes a little bit, okay, because we're dealing with that little distribution. So here's my population. We'll say our population looks like that. And I've got this sample, and we'll say the mean is right there. The sampling distribution of x bar will be looking like that within that population. All right, we've got a bunch of x bars in here. Those are my sample means. Right there. So there's my population of all the raw data. But if I take samples of size 30 or bigger, those sample means will look like this. Okay? So when I use a z-score for this distribution, for that little sample distribution, the z-score is different now. The z-score for an x bar is x bar minus mu all over sigma, seems about right so far, but divided by radical n. That makes the standard deviation smaller, which is true. Look at that. Look how spread out the population was. So to accommodate for that, we want a smaller spread. See how tighter that is? That's going to be a smaller standard deviation. It's not as spread out. So to accommodate for that, that's calculated as the population standard deviation divided by radical n. That's radical the sample size, or the square root of n. Okay? Now, likewise, we have another rule that applies to this. If my population is normal or approximately normal, here's my population. We'll put our mean right in the middle. That it doesn't matter what my sample size is, the sample means will always be approximately normal. So when we don't know the shape, or if the shape is weird, then I have to have at least 30. But if the population is already approximately normal, the size does not matter. Size n does not matter. When the shape is like this, size will matter. And that size must be greater than or equal to 30. 30 is the magic number. Okay? So size matters when it has a shape that's not approximately normal, and it doesn't matter. I can have samples of size 3. It's still going to look like that. It's going to look approximately normal within the inside. Let's try a sample, an example problem for this kind of material. Okay? And let's see what this is like. So this one has to do with movies. All right, so the average movie ticket price is $8.61. All right, let me get a little space here. So the average movie price is $8.61 with a standard deviation ticket price of 1.39. We do not know what the distribution of ticket prices is. We don't know if it's normal or not, okay? But we took samples of size 50, okay? So the question now is, what is the probability that my sample mean is greater than 8? So what's the probability that x bar is greater than 8? What does that mean? All right, so I'm going to make a little sketch here first, and we'll try to make some sense out of this. So I have a population. I have no idea how it looks. I'm just going to draw a random shape. Look at my sample size. It's 50. That's bigger than 30. So since we know it's bigger than 30, we know our sampling distribution of means will be right there. Okay, a couple things to know about that. If my sampling distribution is bigger than 30, well, first of all, the sample means will always be the same as the population mean. Something to know. The mean of all the samples equals the population mean. And the standard deviation of the samples of X bar will be smaller than the population. It has to be, right? Because I'm taking numbers from in this. If I took the largest and the smallest and average, I get in the center. I get a dot right there. If I take those two, I get one right here. I'm not going to get any out here, any observations of sample means way out there. They're always going to be toward the center. So the average of all the X bars is the same as the population. The standard deviation of the X bars will always be smaller, and that number is sigma over radical n. So those are two rules that we have to know, okay? So what's the population that X bar is greater than 8? Well, for my population, we said the mean was 8.61. That's this number right in the center here. That's 8.61. So we're going to say 8 is less than that. 8's going to be right there, okay? So what's the probability that it's greater than 8? Well, that's all of this. We're only messing with the distribution of X bars, not the population, not this. We want this. We're concerned about the little graph, okay? So we need to find the z-score for that 8 and then take the area to the other side of that, okay? So here we go. What is the z-score for 8? So here we go. The z-score for 8 is 8 minus the mean, and the mean is 8.61, divided by this new standard deviation. That's sigma, which is 1.39, over radical n, radical 50. So on the top, I get negative 0.61, and my denominator, which I already worked out, 0.1966. So negative 0.61 divided by 0.1966. If you're playing along at home, try to do that calculation. And when I work that out, I end up getting negative 3.102. Negative 3.102. That's the z-score for 8 as a sample mean. In other words, for that little graph, all right? So with z-score, whereas the center is always 0, and positive 1, positive 2, positive 3, negative 1, negative 2, this is negative, this is way out there, negative 3.102, okay? So now we have to go to our graph, our chart, our left-sided chart, because the negatives are on one chart, the positives are on the other, okay? So when I look at the chart, this is what I want to look at, all right? Negative 3.0, right? Negative 3.10. Negative 3.1, and then 0, right? We're just taking those decimals, negative 3.10. The 2's not going to matter. It's not going to bump the 0 up. And when I do that, I find the value of 0.0010. That's what the chart says. That's small, okay? But that's just the values on the left side. I want to know the right side. So they're complements of one another. It's 1 minus that. So what is 1 minus all of that? Okay, so for right now, we're basing it as z's. What's the probability that z is less than 8? Whoops, I said that wrong. That z is less than negative 3.102. Well, less than is this, 0.0010. But we want the opposite of that. We want the other side, right? We want greater than. So now what's the probability that z is greater than negative 3.102? That would be the complement of this. So it's 1 minus 0.0010. So that this part's from the chart, and this part is the opposite, or the complement. So can you do that in your head, or do you need a calculator? So 1 minus 0.0010, I bet we get a lot of 9s. We get 0.999. 0.999. So 99.9% is on this side. So that's 0.999 or 99.9%. That's the probability that X bar will be bigger than 8. All right? That's the probability that X bar is bigger than 8. So when we have a situation when they talk about the sample means, we now have to look at this amended formula where we have sigma over radical n as my standard deviation. So look for the words sample means. We're doing a problem not with raw data, but with sample means, all right? So when you do that, you have to look for that formula, all right? So I'll have some notes with that. We have a test on Thursday. I would suggest getting a scanning app on your phone because you can take a photo of your test and you can convert it to a PDF and then you can send it off to me, all right? That might be the easiest way to do that. So look for PDF apps on your phone or photo to PDF. There are a lot of them right now. It's very popular because all the kids in school are using it right now for their assignments. So look for an app that changes a photo to a PDF, and then you can send the PDF to me. You can just show your work. You don't have to type out your test. In other words, you can just do it like you normally would in the classroom. So that's my suggestion. All righty?